Mhm. Actually, yes. So this is set up, and I think you can feel free to share the screen or check it. Yeah, you are no. Let me also share. You can actually go direct to.
Let's try. Let me try. Maybe is it okay? You can you see this pointer line? Yeah, it seems good.
I heard from Professor Yao, you are his postdoc previously.
Yeah, long time ago, maybe 15 years ago or something.
And he still remember your work. And also praise, praise about your result.
Yeah, I'm very happy that he remember me. Yeah, that was a nice work, I think. And I could learn a lot from him and people there. So are you also a student of Professor Yao, or?
Oh, no, I'm more like a postdoc.
Oh, I see. So it's like me. And do you have a high energy physics background or condensed matter or mathematics?
I think it's very hard to choose. I don't know how to say.
Maybe some.
But my PhD was on the more condensed matter people. And by the way, someone asked whether it will be recorded. It will be recorded. If it's okay with.
Sure.
And so now you can relax maybe for 5 minutes, and
I
will also
yes.
Another team, and we can meet up in 4 or 5 minutes.
Yes.
And relax. Satoshi? Are you around now?
Yeah, yes, I'm ready.
So maybe let me also record. I think people will just come in, but let's welcome everyone first. Okay, so welcome everyone. Welcome to Harvard CMSA seminar. 皆さん心から歓迎します。It is our great honor to invite Professor Satoshi Yamaguchi to Harvard CMSA seminar. Yamaguchi Satoshi 教授を Harvard CMSA セミナーにご招待できることを大変光栄に思います。And please don't forget to thumb up and subscribe to CMSA seminar. 親指を立てて CMSA セミナーに登録することを忘れないでください。And let's welcome Satoshi for the his topic will be Supersymmetric QFT with exotic symmetry in 3+1 dimensions and the fermionic fracton phases. Let's welcome Satoshi. Please take over.
Okay, thank you very much for introduction. And it's a great honor for me to give a seminar here in CMSA. And thank you very much for inviting me and giving me this opportunity. Today, I would like to talk about this supersymmetric quantum field theory with exotic symmetry in 3+1 dimensions and fermionic fracton phases. And I'm Satoshi Yamaguchi from Osaka University, Japan. And this talk is based on the, my recent paper. So let's start with the introduction. So today, I would like to talk something related to so-called fracton phases. And fracton phases are attracting attention, a lot of attention recently. And the study of fracton phases start from these people. And there are lots of works which I could not list here. And there are also nice review papers on fracton phases. And fracton phases are kind of a quantum system with the following exotic features. And one exotic feature of fracton phase is that the ground state degeneracy of this fracton phase is exponentially large, but the residual entropy or log of the number of ground state is not extensive. I mean, for example, in some system, log of number of ground states is proportional to area and not proportional to the volume. So this is quite an exotic feature and quite an interesting feature for me. And it reminds me that black hole entropy. And black hole entropy is also proportional to the area, and it's not extensive. And studying such fracton system maybe give a hint to understand the physics of quantum gravity and black hole. And the second one is the following. Such fracton phase system includes some particle-like excitation with restricted mobility. So, for example, you may have some particle-like excitation here, and this particle-like excitation move this direction or this direction. But it cannot move this direction or this direction, or some other particle cannot move at all. And such excitation is called fracton, and it's a kind of a very interesting exotic feature of this such fracton phases. And the third one is I think the most important feature or property of this system. And this symmetry, this one is so-called subsystem symmetries, will explain these exotic features. And subsystem symmetry is a symmetry only acts on subsystem, or in other words, for example, some conserved charge is conserved only on this red line, and the charge density can move this way, but it cannot go out of this red line, for example. Such symmetry is called subsystem symmetry, and maybe I will come back to this subsystem symmetry later. And if you heard about some kind of higher form symmetry, then this subsystem symmetry is not something different from this higher form symmetry. And yeah, okay. So I think in this talk, I'm kind of focused on this subsystem symmetry.
Excuse me, I have a question.
Yes, please.
So this subsystem symmetry, do you require it to be exact, or it can be emergent? My understanding is that if you break subsystem symmetry by some perturbation, and the Fracton phase is still there, you don't destroy Fracton phase even when you break subsystem symmetry.
Oh, really? I see.
But by adding, basically, the Fracton phase is robust against any local perturbation. But certainly there's a model with the subsystem symmetry, and so here I just want to make sure. Here you assume subsystem symmetry is exact. It's not emergent symmetry.
Yes, here I want to require our subsystem symmetry is exact.
Okay.
So
yeah, thank you.
Yes, I'm not sure. So in that sense, our Fracton phase, some system in this talk may really robust Fracton phases.
Okay.
At least I just assume require subsystem symmetry.
Okay. Yeah. Thank you.
I suppose
what
yes. the setup that the Satoshi had will be a realization in terms of field theory, and there will be a global symmetry with respect to that field theory, right?
Right.
And
yes,
no problem. And I wonder whether Shogun was meant to say the latest realization, or I suppose in his case will be a field theory realization.
Yes.
Well, even in field theory realization, there's an issue about you can add local operators which break those symmetries, and there's an issue whether this local operator as a perturbation would destroy Fracton phase or not destroy Fracton phase. I think there is such issue, but you can certainly assume you have this exact subsystem symmetry. It's okay. Yeah, there's no problem. Yeah.
In many of the examples, the operator that violates the subsystem symmetry in the low energy theory ends up being irrelevant.
Yes.
Or in many cases, even infinitely irrelevant. In which case, you get it as an emergent symmetry, even if it's not an exact symmetry at short distances.
Exactly. Yeah.
I see. Thank you very much.
And I should mention the audience should feel free to interrupt and make comments, please.
Yes. Please ask questions and comments. And yeah, actually, I'm more interested in this talk. I'm taking a continuum field theory, and of course there are lots of examples and a lot of studies of lattice quantum mechanics models which shows Fracton phases. And some of them are exactly solved, and they have shown rigorously they have the features of Fracton phases. And my question is, are there any continuous quantum field theory description of fractal phases? And of course, there are lots of works related to this continuum quantum field theory. And my impression is that strict continuum limit may be difficult. I mean, in usual quantum field theory, we often consider so-called UV complete quantum field theory. But that kind of UV complete field theory may not show such fractal phases. Because, for example, the number of ground states goes to exactly infinity. And in the usual healthy quantum field theory, in finite volume, has only finite number of states below some given energy. And such fractal phases is in that sense, if it ever exists, it's a kind of pathological theory. But that does not mean this continuum quantum field theory approach is useless. And as a usual quantum field theory, this continuum approach is quite a nice way to consider the universal features independent of the microscopic detail. And some of the features of such lattice system, like exact form of lattice system, or say exact form of the interaction, may be irrelevant to the low energy physics. And continuum quantum field theory approach is useful to forget such detail and focus on the more important features. And in this talk, we mostly employ this continuum field theory approach. And another issue I want to study is fermions. And of course, in condensed matter physics, fermions are quite important. And as far as I know, there are not much works are done in particular in continuum approach with fermions. And there are some fermionic Fracton phases are considered in these papers, and they use lattice quantum mechanics approach. And one difficulty for me to introduce fermion is that there's no nice guiding principle. In such Fracton phases, there's no Lorentz symmetry, and there's no continuous rotational symmetry. So in some sense, you can do anything, and that could be interesting, but I feel a bit comfortable. And I would like to find something natural introduction of fermions. And that's the biggest motivation to introduce supersymmetry. And supersymmetry relates bosons and fermions. So if you choose your favorite bosonic Fracton system, and once you supersymmetrize that bosonic system and get a supersymmetric system, then this fermionic part of that symmetry, but that system should be kind of a natural fermionic Fracton phase or fermionic exotic system. That's my expectation. So what I would like to do in this talk is to introduce supersymmetry, and also look closely at this fermionic part. Okay.
May I ask you, but if it's supersymmetric theory, you're talking about that, normally, you know, there is this kind of statement about zero energy of ground state, and I'm wondering how it fits in your notion of infinite degeneracy of vacuum state, right? Because okay, so vacuum state would be not super singlet, not singlet or supersymmetry?
Yes, I think in ground state, you're asking about the ground state in supersymmetric theory, right?
Right,
and
right.
It,
yeah.
Yes, it usually say usually a singlet, usually singlet of supersymmetry, and but there are many singlets, and it can contain many states. They are not related by supersymmetry.
Okay, I got it. Okay, thanks.
Thank you for the asking. Yes, and the next question is how to introduce supersymmetry. And my strategy is the following. And in this talk, I mostly take this theory, 3+1 dimensional phi theory, investigated by these people. And this is one of the simplest quantum field theory with subsystem symmetry. And they pointed out that this theory is somewhat related or resemble to 1+1 dimensional massless free scalar theory. And this 1+1 dimensional massless free scalar theory is a nice theory, and it is known that how to supersymmetrize this one. And once it's supersymmetrized, then you will get 1+1 dimensional massless free scalar theory plus massless Majorana fermion system. And of course, this massless Majorana fermion system is not quite natural, nice fermionic system. And my strategy is use this resemblance and apply almost parallel supersymmetrizing procedure to this theory. Then you will get something supersymmetric. And I would like to call this is theory a supersymmetric phi theory. And it's made of phi theory, bosonic phi theory itself, and a fermionic system.
Is this a phi theory gapped or gapless?
Gapless, yes.
Oh, I see.
Yes.
So it's
yes.
unusual.
So,
okay.
Yes. So, yeah. Maybe later I will review this phi theory. So, in this sense, this theory is gapless theory with, after I will explain, it contains many ground states.
Excuse me, can I ask a
yes.
naive question? So since the theory is not Lorentz invariant, is
yes.
there like a non-relativistic version of a supersymmetry algebra, or what do you mean by supersymmetric theory?
Yes, by supersymmetric theory, I mean some fermionic, it contains fermionic symmetry, whose basically some fermionic symmetry and the Q square contains, we at least have a Hamiltonian in this symmetry, so Q square contains Hamiltonian plus something.
Okay.
So in this sense, we are taking a we call this one as a supersymmetry.
Okay, thank you.
Okay. And here is a summary of the result. And we take two supersymmetric examples. One is the supersymmetric phi theory, and another one is supersymmetric tensor gauge theory. And I wrote down the action of supersymmetric phi theory. And in this supersymmetric phi theory, it contains lots of large number of ground states, and the log of that number is proportional to the area, and it's not extensive. And in my paper, I also have shown that self-duality, it's also it's an analog of self-duality of phi theory or T-duality of 1+1 dimensional scalar theory. But today, I will not talk much about this self-duality. For supersymmetric tensor gauge theory, I wrote down the action. And in tensor gauge theory, the fracton is often well described by a defect or say Wilson loop. And I will discuss some BPS fractons, which preserves half of the supersymmetry. These are the main result of this talk. And this is a plan. I first review phi theory. And next, I will go to the some result. Before going to the formulation, I will show some results in supersymmetric phi theory. The results are rather, part of the results are rather simple, and maybe people are more interested in those results than formulation. And then I have enough time, I will explain some formulation. And next, I will go to the supersymmetric tensor gauge theory. And finally, I will give some summary of my talk and some discussions. So are there any questions so far?
Oh, actually, can I ask a question about the self-duality? So the boson theory actually has self-duality. So do you mean the supersymmetric theory also have the self-duality or not? I think I missed that point.
Yes, I meant supersymmetric theory has self-duality.
Okay, so including the fermion part also has self-dual.
Could you ask again? Say again.
Oh yeah, just trying to make sure that the fermion part of the theory also self-dual. It also has self-dual, is that right?
No, a whole part has self-duality. Supersymmetric theory has self-duality, and of course, bosonic theory has self-duality. Yes. And okay, so if you limit it to fermionics.
Yeah, right.
sector,
if I just look at the fermion part.
I'm not sure.
Okay.
Yeah, maybe I can say some symmetry as a self-duality, but I'm not sure. Yeah. Thank you for asking. I'm sorry for that.
Oh, probably.
Yeah. Other questions?
By the way, you need to be careful about the time, though, because if you have a material to cover, only have a 1 hour left, so you may need to speed up a bit.
Yeah, yes. Maybe I skip something if I do not have time, enough time.
Not to skip. We want to hear more. So watch.
Okay. Yes. Let's go to the phi theory. And the phi theory is a 3+1 dimensional theory with coordinate. Let's denote a coordinate of 3 spatial dimension by x, y, z, and 1 time dimension by t. And throughout this talk, we always impose periodic boundary conditions for x, y, d. And this phi theory contains one single real bosonic field with periodicity phi, this 2 pi periodicity, and the Lagrangian has this form. And the time derivative part is rather a standard one, but the spatial derivative part is quite non-standard one. It contains 3 derivatives, x, y, z. So of course, it breaks the Lorentz symmetry because time and the space are quite different. And also it breaks the continuous rotational symmetry because this time derivative part is not rotational invariant. And actually, if you introduce this notation, derivative plus minus with time derivative plus minus spatial 3 derivative, then this Lagrangian density can be written as this way. And yeah, so at least superficially, it resembles to 1+1 dimensional free scalar theory, in which this del plus minus is derivative in the right cone direction. So this is the feature what I would like to use in this talk. And I want to explain subsystem symmetry of this theory. And from this Lagrangian density, you can derive equation motion of this one. And just consider a parallel way to the 1+1 dimensional case. We can define this currents from this scalar field. Then this current satisfies this differential equation, which can be derived from equation motion. And I would like to call this differential equation as conservation law. This is a conservation law because of the following reason. This conservation law is written as this way. And let's consider this quantity. This current is integrated over only x direction. So this integration is not for space, but only on this line parallel to x-axis. And actually, you can show that this quantity is conserved or time independent by using this differential equation. If you take time derivative of this one, then you have to get time derivative of this one, and it's replaced by this x derivative, y derivative, and x derivative of something. And this is a derivative of integral of some derivatives, so it vanishes. So it must be time independent. So such charges are conserved within each line parallel to x-axis. So here you can define one charge, and here you can define another charge, and here you can define another charge. Here you can have another charge, and here you can have another charge. And there are lots of conserved charges in this system. Such conserved charges or such related symmetry is called subsystem symmetry. And I would like to count the number of charges of this subsystem symmetry. So if it's strictly continuous, then the number of the number of charges is just number of lines parallel to x-axis. And yeah, if it's strictly continuous, it's just infinity. So we have to consider some regularization. And in a nice regularization, you can count a number of charges. And this is proportional to the number of this charge is proportional to the line, number of lines parallel to x-axis, so the number of such lines. And the number of such lines are same as the number of points on this YZ plane. So it's in some nice regularization, it should be proportional to the area of YZ plane divided by, say, cutoff square. And we also have QXY, QZX charges, which are defined on XY, this line, and this line. And the conclusion here is that the number of conserved charges for this subsystem symmetry is proportional to the area, not proportional to the volume. That's conclusion up to here.
Actually, may I ask what is there a reason why you start with 3+1D? Because actually the simplest similar model is in 2+1D. So if we start with that, can we do the same thing, or is there a special reason to start with 3D?
Okay, 3+1 dimension is the most analogous to the 1+1 dimensions because we use this relation. It's small. So if it's 2+1 dimensions, sorry, some Leibniz rule is this way.
Oh, you want this relation? Okay.
So I want this relation with this plus.
Okay.
So if this is plus, this is almost completely parallel to the 1+1 dimensions. And if this is minus, then you need some another trick. So 3+1 dimensions is most closely to 1+1 dimensions.
But you say you only require another trick, but you mean you can still formulate a 2+1D version of a supersymmetry theory?
Yes, I think so. I have not yet tried much, but I think you can also make supersymmetry in 2+1 dimensions, but you need some trick, I think. Yes. So yeah, here I have shown that the conserved number of conserved charge is proportional to the area. So let's summarize this section. I reviewed the 3+1 dimensional so-called phi theory, and the Lagrangian is this one, and it resembles the 1+ dimensional massless free scalar theory. And we also introduce or impose subsystem symmetry in this theory, and the number of conserved charges of this symmetry is proportional to the area, not volume.
Question?
Yes.
So is it possible to define like a chiral version of theory where you just have partial plus or partial minus, like the chiral version?
Yeah. Yeah, that's a very interesting questions, and I think you can do. I mean, but I have not much explored. But I think it's like a 1+1 dimensional chiral boson or chiral supersymmetric theory, and chiral boson, and in that case you can do it, and maybe also in this case it's very difficult to write down the Lagrangian density. That's a problem, but I think you can define chiral version of the 1+1 dimensions. Sorry, this chiral phi theory in 3+1 dimensions, and I think I expect that it can appear at the edge of the say 4+1 dimensional some gapped theory.
Right.
It's quite analogous to the 1+1 dimensions. Thank you very much for asking.
Okay. Thank you.
Yeah, that's one of my future work. Yes. So are there any other questions so far? Okay, let's go to supersymmetric phi theory. So you know, I just skipped the how to find this action, but just the result of the action. So the supersymmetric phi theory contains, in addition to this phi of phi theory, and another two real fermionic fields. And the Lagrangian density is written as this way. This part is just phi theory, and this part is the fermionic part, and which I would like to call psi theory. And the supersymmetry transformation is this one. And you can explicitly check that this Lagrangian is invariant under this supersymmetry transformation with up to total derivative. And if you know the 1+1 dimensional supersymmetric system, this part is completely the same. But the one difference, the main difference is just this one. Del plus minus is not the derivative in the right-hand direction, but it's combination of time derivative and this third order derivative. Besides that difference, this is completely parallel to the 1+1 dimensional so-called n equal 1, 1 supersymmetry. So let's come to the subsystem symmetry, and because we have supersymmetry, there is a super partner of those currents of subsystem symmetry. And actually, this is the superpartner of this current is nothing but this fermion psi plus minus. And actually, this psi plus minus satisfies this conservation law. This conservation law is actually easily derived from equation motion of this Lagrangian density. Okay. So by by using the same argument, you can show that integration over only a line parallel to the x-axis is a conserved charge. It's fermionic, but it's independent of time, or in other words, it commutes with Hamiltonian. Okay. So what we get in this supersymmetric theory is, in addition to these large number of bosonic charges of subsystem symmetry, there are also large number of fermionic charges, and they are related by supersymmetry. And in particular, number of bosonic charges are equal to number of fermionic charges. And here is one problem that usually regularization of supersymmetric theory without breaking the supersymmetry is very difficult. For example, it's very hard to construct lattice supersymmetry. So here we just assume there is a nice regularization which preserves this relation. Okay. Once you admit this relation, then you can count the number of ground states in this system. And actually, it is shown by these people. Phi theory has unique vacuum, so we just consider fermionic part of this system to count a ground state. Okay. And first, let's count the fermionic charges or fermionic zero mode.
Excuse me.
Yes.
Let me make sure the psi plus and psi minus are just some Grassmannian variable.
Yes.
And then without any, it's not representation in any space-time symmetry group, right?
Right. It's just one component of Grassmann variable. Yes.
Thanks.
So there are just two components of just like J plus minus. There are two psi plus and psi minus. And number of fermionic charges is equal to bosonic charges because of supersymmetry. And I stressed that the number of bosonic charges denoted by A is proportional to the area. So if you use these relations, you can say number of fermionic charges are proportional to the area and equal to this A. And so for notational convenience, let's take some linear combination, or maybe just take some normalization of this one. And let's denote some linear combination by this gamma A with A runs from 1 to A, and such that it has this canonical anti-commutation relations. These charges are similar anti-commutation relations, but this is maybe delta function or something. But by some regularization and change the normalization, then you will get this relation of canonical anti-commutation relations. And this is nothing but a Clifford algebra with A generators. And you also, they are charges, so there is also, they are also satisfied. They also commute with Hamiltonian. So the Hilbert space of the ground state must be a representation space of this Clifford algebra.
May I ask you, but does it mean that, okay, it doesn't mean that you have a number of fermions effectively proportional to A, right? You still, number of fermionic field was still, you know, you have like one fermionic field originally, right? And but here it is like localized fermion, or how you know this now when you are counting this fermionic charges, for example, then each charge corresponds to some kind of fermionic field in certain sense, right? Or it's not the case.
Okay, how to count this area? So
yeah.
naively, this number of y and z. So they are.
I see. No, but
they are a point on YZ plane, and the number of points on YZ plane must be proportional to the area of YZ plane.
I see. So it's like localized stuff, right? That you
yes.
have kind of. Okay, thank you.
As a field, there are only say two, but fields are one field contains an infinite number of fermions, and most of them are non-zero modes, but some of them are zero modes.
Okay, thank you.
And yes. Okay. So the ground state space of the ground Hilbert space of the ground state must be a representation of this Clifford algebra, and it is known that irreducible dimension of irreducible representation of this Clifford algebra is this one, 2 to the A over 2. So, so this must be a number of ground state. So if you know the RNS formalism of superstring theory, then it's the same procedure as you know, number of Ramon ground state. So the conclusion is that log of ground state is written this way, and it's proportional to A, and it's proportional to A is proportional to the area, so it's proportional to the area. So this is one result of this talk, and this supersymmetric phi theory, the ground state has a large number of degeneracy, and its residual entropy is proportional to the area.
Excuse me, a very naive question. So does it mean that the area is quantized, or are there some units hiding there that I'm missing?
Yes, I assume some nice regularization. So for example, if you choose lattice regularization, then the area is quantized. I mean.
Okay, yeah, thank you.
There is some unit area a square. So it's precisely speaking, a is proportional to the area over unit area.
Thank you.
And yeah, and actually, so as someone asked, it's may depends on the regularization. And actually, I'm not quite kind of an expert of lattice system, but I try something to try some regularization, lattice regularization of this psi theory. And this is actually quite naive one, and I'm not quite satisfactory with this one, but I think someone may be interested in such a lattice system, so I want to explain this lattice system here. And I'm considering Lx times Ly times Lz cubic lattice and with periodic boundary condition. And we prepare real fermions at each site. And they satisfy these anti-commutation relations. And Hamiltonian is this one. And this delta xyz is quite naive discretization of this derivative of xyz. And the precise form is this one. I'm sorry for small characters. And this looks like a kind of a, say, some kind of tight binding model. I mean, it only contains a quadratic term in fermionic operators. And actually, for example, this site is interacting to this site, diagonally separated site, and this 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 site, and the other side. And this is not interacting with neighboring site or next neighboring site. This is a system I considered. This is just a naive discretization of the of this psi, half of the psi system. I mean. And of course, this is a quadratic in fermions, so you can exactly solve by Fourier transformation. And by Fourier transformation, Hamiltonian can be written this way. And the B is discretion and annihilation operator. And the dispersion relation is this one. And actually, in this exact, yes.
Thanks. Sorry, actually, I was asking something earlier. Maybe we can go back. But just make sure when you count in this the number of ground states.
Yes.
And related to this Clifford algebra, the number of the subindex. I just want to make sure
this one.
This approximation, in the sense that maybe you need to maybe divide, subtract by 1 or something. Also depends on whether the number of the big A is even or odd.
Yes. This area means just infinite volume limit. I mean this area is just a leading term.
Okay, no problem. So yeah.
Is that your question?
Yeah, I mean there are probably some subtraction you need to, but the dominant term will be this.
Yes. There is some subtraction. Yep. Yes.
Thank you.
I just ignore that one in this rough approximation.
Okay, thanks.
And maybe in this lattice system, you can exactly count the number of ground states. And so let's count the number of zero modes of this system. And number of zero modes is number of k with sine kx, sine ky, sine kz equals 0. So basically, kx equal to for example, kx equals 0 or pi with arbitrary ky, kz. And that one is this term. 2 is kx equals 0 and pi, and the number of ky, kz is ly and lz. So maybe your question is, this is proportional to the area, and this is some subleading terms. And this is actually overcounting, and you have to subtract something. And this is over subtracting, and you have to add something. And I think if I believe I didn't make a mistake, but this is the exact number of zero modes. And by the same argument, you can make a Clifford algebra, and with dimension of the irreducible representation is this one. And this is an exact number of ground states. And actually, this is one, say, quite naive, although it's too naive, but its residual entropy is proportional to the area, and it's not a volume.
Excuse me, does this match to the counting from the Clifford algebra earlier?
The area one is, yeah, this is counting like Clifford algebra. For this counting, let's see.
Sorry, there are two counts. One is counting from the Hamiltonian you write down and find the zero energy modes. And the other is the Clifford algebra that you write earlier.
Clifford algebra. Oh, this is also Clifford algebra counting. I mean, so for such K, BK, sorry, BK commute with H. So, and also this BKs make a Clifford algebra with, they are usually complex, but number of real BK. This is basically K. But some combination of these BKs make a standard basis of the Clifford algebra. And we know that this number is this one, and what we did here is just the same thing. This is just a representation of Clifford algebra expressed by these BKs. Is it the answer to your question?
Well, I suppose yes.
Before we used just continuum field theory, and we did not specify the specific regularization. And in that case, the exact counting of the number of charges is impossible. As you said, you cannot tell what is this one and what is this one. It's almost in the continuum. If it's very large, Lx and Ly, Lz are very large, then you have to ignore this one. This is subleading, the subleading term. So my counting before is just quite rough. And here,
but the leading term match.
Leading term matches up to coefficient.
Okay, thanks.
The proportion to area is area but matches, but for example, this is for example, you made here how you made some numerical coefficient up on this one, and in that case it doesn't match. And so I don't expect that they matches because of the following reasons. And the problem is that some continuum limit, if it ever exists, may or may not be the same as psi theory, continuum psi theory. So because of the following reason. For example, if you only consider the very long waves point, then this sine kx sine ky is kx plus ky, kz. And this is the same one as continuum limit. But this is too naive. And in the if there is also this is a sketch of dispersion relations, although it's 2 dimensions instead of 3 dimensions. This point is like this one. But there is another similar point here and here and here in this picture. And there are another 4 points in 3 dimensions. And those points have similar property by just redefining this wave number. So if you are a bit careful, there are 7 copies of this point, and which are often called doublers in the lattice gauge theory context. And 2 copies of such points make 1 copy of psi theory. So there may be 4 copies of psi theory. If you only count such points, say this point. But this counting is, again, I'm afraid that it's too naive. Because in the low energy, this line, on this line, or on this line, and this line are also low energy. The energy, the frequency is small. So in the low energy limit, those parts also contribute. And for those parts, it's not quite resembles to the continuum theory. So I'm not quite sure that you can take continuum limit in this theory, or say whether this continuum limit is the same one as the continuum psi theory. So this is quite a kind of a say, and not quite satisfactory result. So anyway, I summarize. I will give a summary of this section. I have shown that this supersymmetric phi theory Lagrangian density, and I have shown that the ground states log of number of ground states is proportional to the area. This is a quite interesting properties, and I give an attempt to regularize the psi theory, but it is still an open problem, I think, and it's not so obvious problem. And yes, so are there any questions in this part or other point?
So you still have 3 sections, right?
Right. Yes. Okay, so maybe I have maybe 20 minutes or so. And yes.
30 minutes.
Yes, maybe I think I have 20 or 25 minutes or something, right?
30 minutes.
30 minutes, okay. 30.
30.
Okay, good. So next I want to talk about how to how to construct such Lagrangian. So we employ so-called superfield formalism, and let me briefly explain what is superfield formalism. We introduce real fermionic coordinates psi plus and psi minus in addition to x, y, zt, and consider so-called superfield. And action is written as this bosonic coordinate integral and fermionic coordinate integral, and of some say function or polynomial of phi and its derivatives. That's how we write down the action of supersymmetric. That's one way to write down the action of supersymmetric theory. And I employed this one here. But this is almost parallel to 1+1 dimensional n equal 1,1 superfield. And the content is quite technical, so I don't go into the detail. But there is one difference between this 1+1 dimensional n equal 1,1 superfield and our result. And there is an obstacle. So far, we found that L, this super Lagrangian density, must be quadratic in superfield in order to have supersymmetry. So in that sense, we can only write down the Lagrangian of free field theory in this method. And writing down interacting Lagrangian is an open problem. So maybe I want to skip this one and just to say
but in this sense, sorry to ask, to interrupt. I mean,
let me recommend one thing. You don't worry about time. I think please try to go through it. And
oh, really?
yes. And Arkady, go ahead. Your question.
No. I just wonder that you know, this integration over theta or differentiating over theta is then conjugated to your d plus d minus, right? In certain sense, because the algebra, for example, in terms of say derivative, I mean this super derivative, right, would be the one which would be associated with d plus d minus, right?
Yes. So this integration is basically this integration is just say kind of supersymmetric transformation up to total derivative.
Mm-hmm.
Yes.
Okay, thank you.
Okay, so then I want to explain. So explain why this such difficulty or obstacle comes out. And let's start with warm up, and I think most of you are quite familiar with this one, but I explain this one, how to write down the translational invariant theory. And let's choose local field and consider translation, and how to write down an invariant action under this translation. So if phi and phi 2 are local field, means which satisfies this transformation law, then phi 3, the product of this one, product of two local fields, and also derivative of local field are also local fields. Means these two operators are also transformed by this way. Because derivative is because derivative commute with to each other, so it's transformed as this way. And this product, for this product, if you take the consider transformation of this one. Then you transformation of this one, and this derivative satisfies the Leibniz, usual Leibniz rule, and it can be written this way, and you will get this result. So this Leibniz, satisfying this Leibniz rule is a key feature that this product is also a local field. So product actually satisfies this transformation law, which is the same one as this one. And so Lagrangian density is a local field if it's a polynomial of local fields and their derivatives. So if they're polynomial, then it satisfies this transformation law. And the transformation of this Lagrangian density is total derivative. And this is invariant up to total derivative. And just write down the Lagrangian as a polynomial of local field and its derivatives, then you get translation invariant Lagrangian density. That's how we write down the translational invariance theory. But let's consider some twist of such thing. Instead of usual translation, let's consider this transformation. For translation, this is just one derivative, but you can consider this transformation made by these three derivatives. And let's call this the field which satisfies this transformation law as XYZ local field. And the problem is how to write down an invariant action under this transformation. So is it okay? What is the problem? So if phi 1 and phi 2 are XYZ local field, then the derivatives are XYZ local fields because this differentiation and this derivative commute to each other. But the problem is this one, product of two XYZ local field is not an local field, XYZ local field. Because, okay, this transformation like this one and this one, but this one is not equal to this one because Leibniz rule is not satisfied in this triple third order derivatives. So that's a problem, and they are different. So they are not this one, and this one is not equal to this one. So the transformation is not this one. Transformation law of this one is more, say, messy thing. So that's a problem, and in that sense, arbitrary polynomial of XYZ field and XYZ local fields with under their derivatives are not this transformation invariant. However, this is not a XYZ local field. Still, they are not very complicated. A bit complicated thing. This is not a simple thing, but they are still total derivative. Okay. So if the Lagrangian density is quadratic or lower polynomial of XYZ local field, then L is invariant under this transformation up to total derivative. Everything is okay. Okay, good. So the same problem appears in the supersymmetry transformation. So let's consider supersymmetry. And supersymmetry transformation is defined by this equation. Here Q is some nice differential operator in superspace. It contains the fermionic derivative and the bosonic derivative as well. And the problem is here in the bosonic derivative, you will have this third order derivative. And it does not satisfy the Leibniz rule. Then how to write down the invariant action under supersymmetry? And if phi and phi2 are superfield, I mean, if some fields on superspace satisfy this transformation law, then let's call this one superfield. And if they are superfield, then these derivatives are superfield. This is usually bosonic derivatives, and this D is some nice fermionic derivatives. This is okay, but this is not. This is the main difference between usual supersymmetry and supersymmetry in this talk.
I'm sorry, do these Q's satisfy, what is the supersymmetry algebra they satisfy? What's the
okay.
commutator of Q's? Does it have one spatial derivative or does it have three spatial derivatives?
Let's see, Q plus.
I can't keep track of your plus and minus, but it seems to me that, yeah, so it's not translation on the right-hand side.
Yes, yes, Hamiltonian is a time translation, but this is not translation. That's yeah,
so what
the
is
point.
It?
And this is a generator of this transformation. And if the theory, our supersymmetry theory must have this.
So this algebra is not the standard supersymmetry algebra.
No, you are right. So this is not a standard supersymmetry generator. You know, it's not standard supersymmetry algebra.
But still, D plus, D minus anticommutator, I mean, fermionic D plus D minus would be what? Would be just this spatial D plus minus or what? Because it is, you know, it's essentially the same question which Nati is asking, right? Because the algebra.
Yes, D plus.
Fermionic D plus D minus anticommutator.
This one, D plus D minus, for example, D plus D minus.
Yeah.
Is maybe D plus is the plus basically, and this is the D plus the X there by the.
I see. Okay, so in this way it's like a chiral, right? Because it's only containing D plus. So but then D plus, but then you have similar for D minus, right? And then it will be D minus.
Yes, D minus is minus here.
Yeah, I see. Okay.
And the D plus and D minus commute to each other. And of course we use Q something and D minus anti-commute.
But I don't understand. I don't think I understand this PXYZ as a global symmetry. It's not translation.
Right, this is not a translation.
So what is it? It's not an internal symmetry because it acts on the coordinates.
No, it's not acting. Just we can define transformation of phi by this one.
Right, but this isn't the infinitesimal transformation. How do you exponentiate? Normally,
I'm not
what
sure.
you have there is epsilon d by dx of phi. It's ordinary translation. And then you can exponentiate it and have a translation which is not infinitesimal.
Does it make sense? I think I'm not sure.
You tell me, does it make sense? What does it do to phi?
I don't think you can.
You have only one derivative. What it does, it shifts the argument of phi.
Right. Usually,
Yes,
this first derivative it's just a translation, but this is quite non-local transformation, and this is not a say local field at any other local field, I think.
So the symmetry, so the global symmetry of your model maps a local field phi to a non-local field phi.
Yes. So in that sense, yes. So this is quite non-local transformation, and in the formal sense, you can the Lagrangian density is invariant by this infinitesimal transformation by up to total derivative, and you can find the net charge by usual procedure, and that is this one. And more intuitive or physical meaning of this transformation is I have never seen such transformation in other literature. So I'm not sure what is a physical
no corresponding geometric operation on x, y, and z. The ordinary derivative pushes you in some direction, so it's translation.
Right.
This thing, which is non-linear in the derivative, I don't know what it means geometrically.
Right.
But it's possible to ask in the same a little bit different way. Consider delta square. Consider that we are acting, in this exponent by the second term. So you have dx squared, dy squared, dz squared, right?
Right.
This term would be non-vanishing or vanishing?
In a finite transformation, this is not vanishing.
Yeah, so there is no condition that d square on acting on phi is 0, right?
Right.
I see. Yeah, because then it could be like a fermionic type of transformation, right? If a square would be 0.
Oh, I see. Fermionic type.
Yeah, because fermionic type is the one where you have q square equals 0, right?
Yes, but this transformation is just bosonic one.
Right.
This epsilon is,
No, of course it's bosonic, but if it would be the one where square of which would be 0, then it would be it would look like fermionic. That's why I'm asking, but I'm probably
I see. Thank you. But if it's fermionic, then it will be a local transformation. But unfortunately, it's quite non-local, and maybe it's not this transformation is something what I have ever seen in the literature. But for example, phi theory does have this symmetry actually. So it may part of, I'm not sure, it may part of the symmetry in the phi theory, I guess. Okay, good. So this one is a main obstacle in our formulation. And yes, but this is total because this is total derivative. So if Lagrangian density is quadratic, then we can write down, the Lagrangian density is invariant under supersymmetric transformation up to total derivative. For example, if we write down this one, then this is equal to supersymmetric phi theory I have shown. Okay. So maybe this is an open problem that how to write down some interacting theories. Maybe we need some new idea. Okay, let's summarize this section. So the action is this form, and we have to limit ourselves to the quadratic super Lagrangian density as a quadratic in superfield. And as an example, supersymmetric phi theory is written this way.
Excuse me?
Yes.
About the open problem, just naively, can it be possibly just adding some gauge field and gauge null to a theory to make it interacting theory?
I will next want to tell you the gauge theory, but the action is actually quadratic in this gauge theory, and usual gauge theory is of course interacting, and I cannot consider usual gauge theory in this formulation.
Oh, you say you cannot, you haven't been able to introduce gauge field to the previous section, the one that you.
I can, but it's gauge field for shift symmetry. It's not say usual, I mean, phase rotational gauge field. Maybe I can. I want to explain next what I meant by gauge field. Okay. So final part is supersymmetric gauge theory, tensor gauge theory, and this is supersymmetric. My idea is to gauge this shift symmetry. This theory has this shift symmetry when this lambda is constant because it only contains derivative. And to gauge this shift symmetry. And in order to do it, we promote this gauge parameter to the the superfield, okay, and consider gauge transformation of phi as this way. And we want to introduce so-called gauge field, gauge superfield here, and define covariant derivative as this way. So actually, for usual, phase gauge, phase rotation gauge symmetry, such covariant derivative includes some quadratic term in field. But this is a shift symmetry, so this covariant derivative is just linear in field. So that's why we do not have, say, more than cubic term in the Lagrangian. So anyway, the gauge transformation law of this gauge field can be written as this way. Then this covariant derivative is gauge invariant. And and the things are quite messy, so I want to explain where is tensor gauge field. And in gamma plus you have A plus here, and in gamma minus you have A minus here. In parameter K, you have top component here. Then the gauge transformation of this A component is written as this way. And if you define this AT and AXYZ by adding and subtracting A plus and A minus, then this transformation of AT is rather usual one. But this transformation of AXYZ is quite unusual one. And this is a tensor field considered in these people and other people, I think. So in that sense, gamma plus and gamma minus are supersymmetric completion of this tensor gauge field. And the action is quite standard. The constraint is we only can include the up to quadratic of the gauge, the superfield. This is a gauge invariant, say, kind of field strength. And you can write down the gauge kinetic term and some gauge mass term and BF coupling term. And this is also this is a theta term. And matter part is written as this way. And all terms are quadratic or linear in superfield. So, although this is a gauge theory, but it only contains quadratic or linear term. So it has supersymmetry in our formulation. And finally, I want to discuss something about fractons. And
nice introduction, and for inviting me. It's a real pleasure.
Could you?
Professor unmute himself, maybe for other reasons. So I think.
Okay.
I think. Please go on.
Yeah. Okay. Thank you. And yeah, fracton in tensor gauge theory is described by this way. For example, you can consider some particle coupled to this tensor gauge theory by usual way. But the theory does not include that such particle, but we can introduce some external particle into the theory. That is often called a defect. And you can consider some defect particle at rest, or test particle at rest. It's expressed by this Wilson line. And AT is just A plus A minus. But you can describe this particle at rest by this operator, but this particle cannot move since there's no AXA, there's AXYZ, but there's no AXAYAZ. So you cannot introduce Wilson line like this moving particle. So this defect is fracton. And yeah, it's considered in many people in the context of tensor gauge theory. And I want to consider that the supersymmetry on this fracton. And this fracton breaks all the supersymmetry. And I wonder there is any BPS fracton. And there is, and yes. And if you put one scalar component in the gauge field, then you can show that this operator preserves half of the supersymmetry. And you can say this is a BPS fracton. And actually, if four of such fractons are combined and four of such fractons are combined and make some quadrupole, then they can move to one direction. But as far as I tried, I could not find any BPS analog of such moving quadrupole in our supersymmetric theory. Even if the velocity is constant, it breaks all the supersymmetry. Okay, anyway, let's summarize of this section. We write down the supersymmetric tensor gauge theory. The action is written. And we found that BPS fracton exists, but there's no BPS quadrupole exists. So let's summarize. And we consider two supersymmetric theories, supersymmetric phi theory and supersymmetric tensor gauge theory. We wrote down action of these ones, and we consider the ground state degeneracy of supersymmetric phi theory, and we found that it's proportional to the area. And I didn't talk this one. And for supersymmetric theory, we found that there is BPS fracton as defect, but we do not find the moving BPS quadrupole of fracton in this theory. And there are many future issues. Maybe one issue is lattice serialization of fermionic system. Maybe supersymmetric lattice system is very difficult, but maybe we have some hope to realize fermionic system resemble to our psi system. It can be written. And we only have free field theory in some sense. So how to write down the interacting theory? And I think someone asked a question, and maybe there is a chiral theory. It's similar to 1+1 dimensions, and maybe it's very interesting to consider such things, and their anomaly. And maybe putting this such theory on curved space may be interesting. And in some literature, I found that some patchwork of this rectangular things to make some, say, to make non-trivial topologies and so on. And if we consider n equal to 2, theories and twist, then we find a topological field theory, and it only contains very large number of ground states, and there's no excited states because it's topological. And it may be useful to consider in the context of say topological field theory, and also condensed matter physics. And I stop here. Thank you very much for the attention.
Thank you very much. ありがとうございました。山口聡教授。素晴らしいセミナーをありがとうございました。Any questions, comments? Please feel free.
I have a question. It's a very interesting proposal. If I understand correctly, your main result is that the ground state degeneracy is proportional to the area. Is this right?
Yes, that's one of the main results.
But then you have that just in the free fermion theory. So you don't need, or what does supersymmetry buy you in this case?
Oh, okay, good. In that sense, supersymmetry is how to find that fermionic Lagrangian density. If I don't consider supersymmetry, it may be not easy to find that fermionic Lagrangian. But I don't, in that sense, right, supersymmetry does not play much role.
I actually maybe can follow this. I'm not sure. So I wonder whether there are people do fermionization or bosonization in the context of finding fermionic fracton systems. Maybe people in the audience can comment. I'm not aware.
Yeah, I want to.
That could be another way.
Someone may have some comments.
Actually, I think back in the days, I thought about fermionize this 2+1D gapless fraction model, but actually it will be fermionized into a interacting fermion model, like for example, this ring exchange involves 4 bosons on the lattice, it will fermionize into 4 fermions on the lattice. Actually, yeah, right. That transformation is probably not analogous to this supersymmetric transformation mentioned here.
But these are the lattice approach.
Yeah, that's a lattice approach. Yeah, right. Well, I mean, in 1+1D, the lattice fermion, bosonization, and field theory, they are pretty similar. So.
Yes. Yeah, thank you for the comment. Actually, I'm not quite sure about what you are saying in the lattice formulation, but yeah, that sounds interesting.
But sorry, but Chen-Ke, you also get a fermionic fracton system in the end after.
Well, I need to think about that part, because back then, the concept of fracton was not developed yet. So, yeah, sorry, I need to think about in what sense that's certainly it has some subsystem symmetry, definitely, yeah. I need to think in what sense that's a fracton state.
Yeah. Anyway, thank you very much for the comment.
I have a question about your lattice realization.
You mean lattice realization? Yes.
Yeah, the Hamiltonian you wrote down. So does the model needs to have a line symmetry, right? So how is that defined in your lattice model? It has to have some conservation of like fermion parity on individual lines, or something like that, or fermion number.
Sorry, could you ask the question again? So what's symmetry? Fermion. Okay, so
I guess there should be some conservation law of fermion number along each line, individual line, or something like that.
Yes. Maybe some.
Yeah, I'm not sure I see that.
Yeah. So for example, the summation over all line, say, some line is some fermion charge, say Q. And I think this commute with Hamiltonian, and this summation is nothing but choose this Fourier transformation with kx equals 0, for example. And that's how that fermionic charge is realized in this lattice formulation.
But you have psi plus. So psi plus is real field, or psi plus is it's Majorana field, right? Or what?
Yes.
So psi plus is real, right? So
right.
Fermionic charge is combination of psi plus and psi minus. You mean this one?
No, we fermionic charge in continuum theory is just psi plus integration over some line.
I see.
Sorry, maybe let me ask something. You mentioned about the BPS fracton.
Mm-hmm.
Say the combination of 4 fractons. Okay.
Yes.
But the combination of 4 fractons here means BPS fracton, or what? A combination.
Yeah, combination of 4 in the use this fracton if you combine four of them in XY plane, for example.
Okay, but I see. And there's a BPS analog for this, or no?
There is BPS analog for this one. Four of them can have the same half of the supersymmetry, but once it moves, four of them can move to Z direction, for example, at the same time. But this moving for fracton cannot have any supersymmetry. Cannot preserve any supersymmetry. As far as I tried. Even if this velocity is constant. So I mentioned this one because in the Lorentz invariant theory, of course, if the velocity is constant, it's the same one as the particle at the rest, and it preserves also if velocity is constant, then it preserves some half of the supersymmetry. But in this fracton case, once it moves, even if the velocity is constant, it cannot preserve any symmetry.
Oh, and if it doesn't move, then there's still BPS analog.
Yes, just for fractons at rest, preserved half of supersymmetry. Yes.
Thanks. Then I know what you mean by the last sentence you write. You said there's no BPS analog for.
I see. I see. BPS.
Oh, thank you.
Okay, so moving.
Any more questions? Or maybe let's thank Satoshi first. 素晴らしいセミナーをありがとうございました。Thank you very much.
Yeah, thank you very much for attention and lots of.
Yeah.
Hi.
Yeah. Satoshi, long time no see. Thank you for giving the talk. Nice talk.
Thank you for the invitation.
Yeah.
Very nice talk.
Yeah. Thank you.
Thank you very much for Nati. Yeah.
Okay. Hope to see you sometime physically.
Yeah. I hope so.
Yeah. Okay. Thank you very much. Yeah. Bye-bye.
Thank you very much.